Well, we've so far discussed a few operations you could do on vectors, and we talked about a way to, quote, multiply vectors, and that was the dot product. And what was special about the dot product is that you take two vectors together and you get a scalar when you, quote, multiply them. Well, what if you wanted to multiply vectors together and get another vector as a product? This here is the cross product, okay? And sometimes it's actually called the vector product. So you get a vector at the end when you multiply these two vectors out. So a vector has both magnitude and direction. The magnitude of the cross product between u and v is going to be the magnitude of u times the magnitude of v times not cosine theta, which was the dot product, but sine theta, okay? Still, theta is between 0 and pi. And so that's the magnitude of the cross product. And in what direction is it? It's given by the right-hand rule, okay? And the right-hand rule, how that works is you point your hand along, say, we're doing u cross v, so you would point your hand along u, the first vector, okay, and curl it towards v, the second vector, and your thumb, which in this case would point into the page, is u cross v. Okay, that's the right hand rule. It's quite difficult to visualize on a paper, but you just point your hand along u, curl it towards v, and your thumb should be pointing down if you did that right. Okay. Some remarks. U cross v, so this is a whole vector now. So we've crossed them together. We got this vector. It's the vector u cross v. Its dot product with u is 0. Now, what does that mean since we've become experts at the dot product? That means that u cross v and u are orthogonal. They're perpendicular. Not only is the cross product uv orthogonal to u, but it's also orthogonal to v. So u cross v, the cross product, is perpendicular to both u and v. And if u and v aren't parallel, which would give us a cross product of 0 because sine of 0 is 0. So if u and v aren't parallel, then they're going to have they're going to span a certain plane. What this is telling you here, ladies and gentlemen, is that the cross product is perpendicular to the plane that the two vectors u and v would span. So if there is a plane that u and v live in, the cross product has to point in or out of that plane. It can't be along the plane. It's perpendicular to that plane. And what is it going to be? Is it going to be in or is it going to be out? Well, that's the right-hand rule. So u cross v would cause our thumb to point into the page. V cross u is going to have the same magnitude, right? V cross u would have the same magnitude, but now you rotate your fingers from v to u and your thumb should point out in that case. Okay, so it should point out of the page in that case. And so we have this other remark that says u cross v is equal to minus v cross u. So the cross product is not commutative. That minus sign means sometimes it's called anti-commutative. So you keep the same magnitude, but you flip the direction when you change the order of these two vectors. So let's talk a little more about the interpretation of this, okay? The interpretation of the cross product is that its magnitude is the area that a parallelogram would have if you had sides u and v. So here we have the vector u, here we have the vector v. And if we also create a side with the vector v on the top of u, so and also move u down here to create our parallelogram, well, it's going to have a height of u sine theta there. And so this term is actually the area of a parallelogram that u and v would make. Now, physically, how could you think about the cross product? Well, we have this concept in physics, which is also important in our class, called the cross called the torque, and it's the cross product of R, where you would say apply a force and the force. So R cross F gives you the torque. If we have, say, a screw over there and we have a wrench, this is supposed to be a wrench at least, and we let this be our origin, then we have a vector R that points along the arm of the wrench. And suppose we apply a force F that makes an angle theta with R, then the magnitude that we would get by taking the magnitude of R and F times sine theta is going to be the magnitude of the torque. And where would the torque point? In this case, it would point inwards, okay? So R cross F would point inward. And notice here, sine theta, what's the most that sine theta can be? The max it could be is 1. And when is it 1? Well, it's 1 when theta is actually 90 degrees, so pi over 2. Okay? So when R and F are orthogonal, the magnitude of the cross product will be the maximum. Okay? So whereas the dot product was a measure of how much two vectors are along, how much they're along each other, how much they point towards each, in the same direction. The cross product's the opposite. It's how perpendicular it's a measure of how perpendicular they are, in the sense that the more perpendicular they are, the larger the magnitude of the cross product between these two vectors would be. And again, if you want to be efficient and put the maximum force to screwing down a nut, then you're going to want R and F to be perpendicular. You're going to want your cross product to have a maximum magnitude. I mean, why would you be pulling a wrench this way? That doesn't make sense. It's not going to screw anything. The opposite. You want to have it be perpendicular to R. So the concept of the cross product is useful in this regard. So let's take a look at an example here. Find the magnitude and direction of R cross F if R is 110 and F is 1 square root of 2, okay? So F points a little more along the z-axis than R does. So here's our R and here's our F. Well, we're given decent components, and in just a few moments I'm gonna let you know how to work directly with components. But the way we defined it so far was just with the magnitudes and angles. So how do we find, don't cheat and just look. How do you find the angle between two vectors? Well, you use the dot product. Remember that? So if we do R dot F and divide by the magnitudes and take R cosine, just like I did in a previous video, then you would get that theta is equal to pi over 4, okay, which is 45 degrees. And so the angle between these two, this theta over here, is 45 degrees. And so the magnitude of R cross F is going to be the magnitude of R times the magnitude of F times sine of the angle between them, which is pi over 4. Well, what's the magnitude of R? The magnitude of R is the square root of 2. What's the magnitude of F? It's 2. And here, of course, I'm just skipping over these details since you could easily reference them by previous videos, how to find the magnitudes of vector. So you then get that the magnitude of the cross product is 2. That's not the cross product, that's the magnitude of the cross product. Now, what is the cross product? It's a vector. So it's a vector of magnitude 2. And what are we left with to define a vector? A direction. So where does it point? Here, we're going to use the right-hand rule. Here's our vector R. It lies in the xy plane because it has a component of z equal to 0, so it's lying on that plane. And here's F that's directly above it, but with 45-degree angle between them. Curl your fingers from R to F, and your thumb, by the right-hand rule, should point in R cross F, okay? So that's that's as good as we could get with the formula that we used. And of course, that's limiting because the next question should be, well, what is that vector in component form? That's where we're going to need this next theorem here. So this theorem here allows us to compute the cross product and get it in vector form, okay? So that we're not stuck with dealing with the magnitude and right-hand rule. If you have a vector u and a vector v, and both of these live in R3, technically the cross product only exists with vectors that live in space R3, okay? You could kind of extend that by thinking about, to two dimensions, in the sense that you could think about the z component as being 0 of vectors living in the plane, but then it would actually be vectors in R3. So it really just exists in R3. Okay, so we'll have vectors of 3 components, and here's what you do. You take I hat, j hat, and k hat, and what are those? Those were the special unit vectors, okay? This I hat is a vector with magnitude 1 that points in the x direction. This is magnitude 1 and points in the y direction. And k has magnitude 1 and points in the z direction. It's, for example, k is just a vector with 0, 0, 1, where 1 is in the z component. And these bars around is telling us to take the determinant of this matrix. Now you might say, well, how the heck are you plugging in a vector into a matrix like that? This is symbolic, okay? This is just for the sake of memory. And it works formally, even though it really doesn't make sense to plug in a vector like that. But for the purpose of, just remembering and writing in a succinct manner, this would work. So let's take the determinant of this guy. You probably forgot to take determinants of 3x3 matrices, no problem. How you would do so is you mark out the row and column, and that would give you, when you do that, you cross at the I, so this is going to be an I out there over here, and then you're left, if you mark these two out, you're left with this square right there. Well, that's the same square that you get over here, and then we're taking the determinant of this. Now, how do you take the determinant of a 2x2 matrix? Well, that one's easier. You just multiply the diagonals, so you'll have u2 times v3 minus u3 times v2. Okay, and this is just to jog your memory. Okay, there's many resources that could remind you of the taking determinants of 3x3 matrices. Now we're going to jump to this. So that was just this one, right? You cross and you're left with this square. Now we have a minus. Why minus? Because when you're taking determinants of 3x3 matrices, you alternate pluses and minuses. And now we cross out this column and this row, and we're left with u1 and v1 and u3 v3. That makes up that square there. And if we find the determinant of that, that's u1 v3 minus v1 u3, and that's that over here. And finally, you could mark out this column and that row, the first row, and you're left with this guy there for the determinant. And taking the determinant of that, that's u1 v2 minus u2 v1, and that's what you get here, and this k hat. Now, you could just memorize this if you want, okay? To me, I always find it more difficult to memorize things than to just kind of write them out and just compute the determinant. But you could memorize it at this point. This is a formula, and we could write vectors in this way, Uh, this is the special unit vector that has just a 1 in the x component. So you could, um, simplify this if you will, and just end up taking whatever is in the x component and putting it in the x component of your angled bracket expression of a vector, and take minus of this, right? So you have a minus sign, don't forget about that. And that's where you would get this term here, and we'll put it in the y component. And we have a k over here. And I mean, once you get, so you could see vectors either like this, or you could see them in the angled. But you ought to be comfortable with both expressions. This, just think about it as taking it and putting it in the z component, and taking this and putting it in the x component. Taking this, not forgetting of course the minus sign, and putting it in the y component. So whatever you see in front of a j, that's the y component. Whatever you see in front of the k, that's the z component. Whatever you see in front of the I is the x component. And I mean, of course, this works. Maybe it's worth going into just for 1 second. If you have I hat plus b j hat, these should be hats, plus c k hat. Well, that's the same as, say, a 1 0 0 plus b 0 1 0 plus c 0 0 1. Well, what do we get when we simplify? So what are you going to do when you multiply this a through the vector I hat? You're going to get a 0 0 just from scalar multiplication. Do the same thing with that second one. You're going to get 0 b 0, and then c is going to be 0 0 c, again, because you got to just distribute. You could think about it as sort of distributing the c into the vector there. So you're left with adding, okay? And when you add, you're going to get a plus 0 0, so a plus 0 plus 0, and that's just a. And then you'll also get 0 plus b plus 0, and that's just b. And then you'll get 0 plus 0 plus c, and that's just c. So the moral of the story is that if you see a vector, with the angled brackets a, b, c, well, you should think about it exactly the same way as this guy, okay? So what I did with this line here is just translated into the kind of angled bracket representation. They're not different at all. You'll see both of these expressions throughout the class. Sometimes it's just easier to write vectors in a certain way, and so you should get comfortable. And as soon as you see something in front of the I hat, you say, okay, that's the x component, and be comfortable with both of those expressions. Well, we could use the cross product now to find areas of triangles, okay? So suppose you have a triangle that has vertices O, and O here in this class will represent the origin, or the 0 0 0 point. P 2 3 4, it's up here, and Q 3 2 0, it's down here. I couldn't quite draw the triangle. If we're staring down at the triangle, this is what we would see, and I'll just kind of exaggerate it a bit to hopefully make it look more like a triangle. Well, didn't really look more like a triangle, but you get the point. This is actually a triangle, that we're kind of staring down at. And if we want to find, let's find the area of that triangle. And it would be a nightmare trying to find the area of this triangle. It doesn't really have any nice angles to work with. But we could do so by taking advantage of the fact that the cross product, its magnitude, is the area of a parallelogram. So if I'm going to look at this triangle this way, okay, so I'm going to now draw O, Q, and P. Okay, that's the points. Well, what then is the cross product if we take the vector OP and the vector OQ? What are we going to get as a cross product? We're going to get the area of a parallelogram that they make. Okay, so that would be this whole guy here. The cross product's magnitude is going to give us the area of that whole blue space that you see. Well, you don't want the area of this blue, you just want the area of the triangle. Well, that's going to be half of the area of the parallelogram. So here's the strategy. We're going to find the area of the parallelogram. How are we going to do that? Well, we're going to do that by taking the cross product of OP and OQ, the vector that, goes from OP to OQ, from OP and, curls to OQ. And we're then going to divide the area of that parallelogram by 2 to get the area of the triangle. So we have OP here. And how do you find OP? Well, you're going to do 2 minus 0. That's that right there. 3 minus 0. And 4 minus 0. So you get 2, 3, 4. And OQ is 3, 2, 0. In much the same way. Someone might have thought, hey, well, all you did is take that point and just put angled brackets around it. I mean, yeah, that's true. That's what happened at the end. But we distinguish between points and vectors to be very formal, so that you don't just take a point P and convert it to a vector. No, if you want to convert it to a vector, you look at the vector that starts at the origin and goes to the point P and lives in the vector space. Okay, so we have 2, 3, 4, 3, 2, 0. And imagine if you were given a problem where one of the points isn't the origin, then you do have to go through that formalism. So the area of the parallelogram, well, that's going to be the magnitude of the cross product. So let's compute the cross product. Here we will have OP, that's 2, 3, 4. And here we'll have OQ, that's 3, 2, 0. And now we just got to take a 3 by 3 determinant. Cover this guy, cover that guy. That's the I hat component. You're left with this. Multiply the diagonals. 3 times 0 minus 2 times 4. Well, that's negative 8. Minus. Why the minus? Because you have to alternate when you take determinants of 3 by 3 matrices. You have to alternate signs. So you get this J hat. And you would be left with these term. So you'll have 2, 3, and 4, 0 there. That's 2 times, so to get the determinant of that smaller submatrix, you would go 2 times 0 minus 3 times 4. That would give you negative 12, but don't forget the minus, so you get plus 12 at the end. And you do the same thing for the k component. You're left with this vector, and that should be good enough, okay? You could just leave it. That's an answer. But if you like angled brackets more, you could then just write it in terms of angle. So whatever you see in front of the I hat, you just consider the x component, and on and on. Okay, so now we have a vector, and what's the magnitude of that vector? Well, we said the magnitude of the cross product is the area of the parallelogram. So then we're going to take its magnitude, and now we have the area of their parallelogram that OP and OQ would make, and that has a magnitude of square root of 233. That's the area of the parallelogram that OP and OQ would make, but that's not what we're after. What we're after is the area of the triangle, so that's going to be half of that area. So we're left with this red part, and so we take that and divide it by 2, and we are done.